Hi, my name's Jolene. So today in class we wrap up week 4 serial, which means we are done with the fundamental block, lesson 4.1 and 4.2 together, give you the full conceptual framework for what testing actually is before we get into the hands-on stuff in week 5. And for I3, we produce 4 deliverables and commit them on to the GitLab. Include 2 defect report on real-world disaster and STLC checklist and a V-model mapping exercise. They all tell one story, what professional testing look like and why it matters and what happened when it is skipped. Let me walk through all 4 quickly and connect the dots. The Boeing 737 MAX had a system called MCAS. It automatically pushed the nose down if it saw the plane was stalling. The problem is it array from the one sensor, one, no cross-check. When that sensor malfunctioned on 2 flights, MCAS pushed the nose down repeatedly, overpowered the pilot, and the 346 people died. The defect report captured this precisely. MCAS blindly trusts a single cropped AOA sensor, triggering repeated nose-down command that override pilot inputs. Root cause phase is requirement, not coding, not testing. Requirements. MCAS was deliberately classified as a minor low-risk utility to avoid expensive pilot retraining. That classification meant no sensor crossing check was ever required. The disaster was designed in before a line of code was written. Validator Principle 7, absence of error of fallacy. The test passed MCAS execute trim command correctly on the normal input, but nobody asked what happened when the sensor lied. Passing tests on a broken specification is not safety. What we to do differently as a tester is require dual sensor crossing checking in the requirement from the day one. Run mandatory fault injections, feed crop the sensor data into every build and assert system disable graceful. Note that it ignore the fault and put an independent safety review in the room who can say no regardless of the commercial pressure. And the CERC 25 was a cancer radiation machine in 1980s. Earlier model has physical hardware interlock, a mechanical lock that physically prevents the high energy beam from firing without the right shielding in place. The CERC 25 removed those interlock and replaced them with the software. There was a race condition in the software. If an operator typed parameters quickly, which is normal, the software's internal state fell out of sync. The machine showed the electron mode but was armed with full X-ray beam. If fired, patient received hundreds of times the prescribed dose, 3 die. The error message on screen said malfunction 54. Race condition triggers the catastrophic overdose when repeat operator added bypass, remove hardware interlocks. The root cause phase is design and coding. The architecture decision to remove hardware interlock was never formally risk analyzed. Legacy software from an older model was reused without being revalidated for an architecture that had a strip out of hardware safety net that made it safe the first place. They validate principle 1, testing show presence of a defect. Operators across multiple clinics will report malfunction 54 errors. Those reported were dismissed as a minor glitch. The signal was there, but nobody followed. What would I do different as a tester is never remove a hardware interlock and replace it with software alone. Software can fail into lethal state. Hardware fails into safety state. Require formal concurrency analysis before any concurrent code is written. And the test will happen when the operators work at a normal speed, fast speed, and change their mind mid-entry because a medical device cannot be safe only for a textbook perfect behavior. The both cases share the same pattern. The defect start before the code exists. In the requirements for Boeing, in design for CERC, both systems passed their tests. Both had a warning sign that were dismissed. That's not bad luck. That's what happens when the testing process doesn't ask the right questions. So how do we build a process that will have caught these things? That's exactly what the sixth phase of the software testing lifecycle tells us. The phase one, requirement analysis. RTM is required when Boeing failed. An independent tester reviewing MCAS requirement in phase one should have flagged this system can override pilot control. That's not a minor utility. It needs single point failure analysis, flag ambiguity before it becomes a defect. And phase two, test planning. Test plan defines scope, approach, resource, risk. Write what's out of scope explicit list. It protects you from being blamed for things never planned to be tested. And phase three, test case design, test case plus test data. Sarah needs adversary test case, fast operator input, concurrent state transition, file injection. None of that was written. And phase 4, 5, 6, setup, execute, and closure, environment readiness before you run a single test. And the second I35 is the V model exercise. The critical point is timing. For every phase on the left, the test specific should be written at the same time, not after code is done. Apply this directly to bowling. If someone had a written acceptance test specification while MCAS requirements were being written, they would have asked, how do we test what happened when the sensor failed? 4 files, 1 story, Boeing and Zurich show what the cost of the skipping this process look like when the stakes are real. The STLC checklist is the structure that prevented. The V model is the timing, discipline, and enforced. The vocabulary we built this week. Defect report, STLC phase, V model, testing principle. It's the difference between testing that produce a pass report and the testing that actually make a system safe. Thank you for listening.